Hello everyone. Spectroscopy is a physical technique that helps us to understand about the various aspects of any chemical entity, especially the molecules. Before entering into one particular spectroscopic technique, it would be very useful if one can understand all the basics of spectroscopy. So this video will give you the basics of the spectroscopy. What are the different types of spectroscopies that are present, the source, what is the name of that particular spectroscopy, and what exactly happens within the chosen molecule when a particular electromagnetic radiation is being given. So let's get started with the basics of spectroscopy. Well, the classic experiment with a triangular glass prism by Isaac Newton is considered as the first scientific study of spectroscopy. My subject of concern is about molecular spectroscopy, and therefore I will restrict myself to the molecular interactions with the spectrum. To define the molecular spectroscopy, it can be said that it is the study of the interaction of an electromagnetic radiation with the matter that we choose. So before getting into any spectroscopic technique, one should have an idea about the electromagnetic radiation. An electromagnetic radiation is considered as a simple harmonic wave that can propagate through space by a sinusoidal trace. So if I choose any electromagnetic radiation, what it is made up of? Well, it is made up of two important components. One is called as an electric component and the other being the magnetic component. These two components I am trying to illustrate for you. Well, the one in blue, I am considering it as an electric component, and that is let me consider it as a magnetic component, and the one in red I'll consider it as an electric component. So the blue one, let me consider it as a magnetic component, whereas the red I'm considering it as an electric component, and both these components are found to be perpendicular to one another. Also, they are perpendicular to the direction of their propagation. Well, their relation can be seen from here. If this is the direction of propagation, this one is magnetic component and this one is the electric component. All the three are perpendicular to one another. Whatever electromagnetic radiation that we choose, the energy carried by these radiations is quantized, where every quantum of radiation is considered as a photon. So I'm just considering these as photons and they travel with same velocity. So all types of radiations that one chooses, they all travel with the same velocity. Now, whatever electromagnetic radiation that one chooses, it can be characterized by some parameters, and these parameters can be given as wavelength, which I can call it as identity, wave number, and also frequency. Energy for any radiation is also important, that will be discussed later, but the identity for any radiation is given by these three parameters. One we call it as a wavelength, the other wave number, and the third one being the frequency. Let me begin with the wavelength. Wavelength is considered as the distance between two similar consecutive points. So for the wave that I have chosen, now these points can be called as crest, these points can be called as troughs, and the distance between these crest or the troughs is considered as wavelength. Or to that extent, you choose any 2 points that are similar and consecutive. The distance between any 2 similar consecutive points can be considered as wavelength. I am just repeating the point. The distance between any 2 similar consecutive points can be considered as wavelength. So I can choose any two similar points and the distance between them is taken as lambda. Apart from this wavelength, we can also see one more aspect, which is called as the amplitude of a particular wave. So let me show you these things. Well, these are the amplitudes, and yeah, this one is wavelength, or the distance between troughs is wavelength, or I'm choosing these 2 points that are similar and consecutive, or these 2 points, or these 2 points, these 2 points, or these 2 points. Any 2 points that you can choose similar consecutive, that gives you the wavelength. Wavelength is denoted by lambda, as it can be seen, and the units for wavelength is taken in meters, that is the standard unit, along with the meters. Well, we can also have centimeter, micrometer, or nanometer. The next parameter is wave number, indicated by nu bar. This can be defined as the reciprocal of the wavelength. So it is just the reverse of it. You can call the total number of waves passing through a space of 1 centimeter. So within this equation, it can be seen that the wave number is the reciprocal of the wavelength. So when I consider even the units, whatever units that we choose for wave number are the reciprocal units of the wavelength. If I choose centimeter for wavelength, that becomes centimeter inverse. And if it is meters for wavelength, that becomes meter inverse, and so on. For infrared spectroscopy, the most convenient unit to indicate the peaks are these wave numbers. Unit in the sense, the character for a radiation is chosen as wave number instead of the wavelength or frequency indicators. After wave number, the another identity for a radiation is the most important one, the frequency. Frequency indicated by nu. Well, it is defined as the number of waves that pass through a point in 1 second. It is expressed in cycles per second, CPS, or hertz. Well, the relation between the frequency and wavelength can be given as nu equal to c upon wavelength, or lambda, where c is the velocity of the electromagnetic radiation. So from this relation, it can be seen that as, say, these are the inverse relation, as frequency increase, wavelength decrease, or if wavelength increase, frequency decrease. So we can conclude that if greater is the frequency, smaller will be the wavelength, and the converse is also true. The next aspect of an electromagnetic radiation is related to the energy. Whatever molecule that one chooses, there exist different energy levels. It could be nuclear energy level, or electronic energy level, or vibrational energy level, and so on. All these energy levels are quantized energy levels. So suppose I choose these are the energy levels where the energy scale is increasing. This is the energy scale. When I say that the energy levels are quantized, then these energy levels can also be numbered. So let me choose an example of two energy levels, E1 and E2, and this being the energy difference. Well, this is given as E1 and this is given as E2. So whenever the molecule absorbs energy, it is going into upper state, or it can release energy and then it can come to the ground state. here I can consider E1 to be the ground state, whereas the E2 to be the X. So once any molecule that is present in its ground state energy level, as it absorbs the radiation, the one that I have shown in yellow, it will undergo a transition into a higher level, or it may give away some radiation to come into the ground level. All this will happen with some relationship. It is not that it can give any amount of energy or it can take any amount of energy, but this energy is quantized. And how is this energy difference between the two energy levels related? It is given by a classical equation. Here is the equation. The difference of energy between the two energy levels equals h times the frequency, where h is considered to be the Planck's constant. So this could be given in joules, right? So whenever this amount of energy is taken, then transition will occur from one energy level into another energy level. Well, now let me show when a molecule absorbs energy in the ground state, it will undergo state, or from the excited state it can give away energy and come to the ground state. Let me put it in a different way. When a beam of monochromatic radiation is given with a frequency nu, the molecule that is present in its ground state E1, it will absorb the energy and it will transcend into an excited state energy level that is indicated by E2. Alternatively, the molecule from an excited state energy level, it may revert back to the ground state by emitting the same amount of energy. Such a shifting of energy levels upon absorption or emission can be referred as a transition. Well, these transitions, whether it could be an upward transition or it could be a downward transition, they form the basis of a rule called as a transition rule. This transition rule is popularly called in chemistry as selection rule. A selection rule is a quantized rule that gives an idea about the probability of a transition from one quantum state to another quantum state. So this rule is giving you an idea about a transition, whether it occurs or not. If at all it occurs, what is the probability of it? So it has included a term called as probability. Depending on the probability, we can also classify the types of transitions. Well, based upon the intensity of probability, I can call a transition to be with a very high probability, or the transition could be with a very low probability. Sometimes in some spectroscopic techniques the probability is nearly zero. So this particular term we can call that the probability is low to nil. When the probability is very high, we call such a transition as an allowed transition. On contrary, if the probability of any transition is very low, we call it as a forbidden transition. So this is about the identity of an electromagnetic radiation. And as I said, any magnetic radiation could be chosen based on its frequency or on its wavelength. The wavelength may increase or the frequency may increase, that give rise to different types of radiations. Now let me show you the different types of radiations that we very often come across. Now here you can look at the wave pattern. In the beginning, the wavelength is found to be very less, but as it proceeds, here you can see that the wavelength is found to be very high. So when the wavelength is very low, it indicates that the energy is very high. And the electromagnetic radiation with the highest energy is gamma ray. In some old literature, you can also find cosmic ray to be the highest energetic electromagnetic radiation, but now cosmic rays is no more considered as an electromagnetic radiation, and hence we have to consider the gamma ray as the strongest or the most energetic electromagnetic radiation. The consecutive radiations now I am giving you. After gamma ray is X-ray, far UV, UV, visible, near IR, mid IR, far IR, microwave and radio waves. So here I have also indicated the frequency in Hertz. You can see that the frequency is very high for a gamma ray, or you can also call that the energy of gamma ray is very high. But as I proceed towards the radio waves, the frequency has dropped. On contrary, when we look at the wavelengths, the wavelength has been given in meters. The wavelength is very low for a gamma ray, but as I proceed towards the radio waves, we can see that it is in the magnitudes of 10. So the wavelength is increasing when we proceed towards the radio waves. This is all about a few basics of spectroscopy. In my next video, I'll also give you some introduction about different spectroscopic techniques depending on the radiation, and what are the sources, what are the applications of each and every spectroscopy will be given in a single slide. Thank you.